Welcome to week 3. We're going to be doing lab 2 this week, and I wanted to show you another way to navigate in the course from the home page. There are quick links to the modules, and so you can open up the modules here in the table of contents, but as we add more and more modules, you may want to go directly to that module each week. A module will open up, and for this week we're going to be going to the Lab 2 module, and it will take me right to that portion. At the beginning of the course there's only 1 or 2 or 3 modules, but as we go along in the course there will be more. With the other modules you have found that there is a welcome page and introduction materials. This week what I'd like to do is show you how to interact with a PowerPoint. So the PowerPoint will be here in the module for you. You will recognize that this file is accessible for you to look at anytime by this paperclip symbol. If you hover your mouse over it, you can see that it tells me it's an attachment. I'm going to go ahead and open that PowerPoint, and I'm going to do the introduction for you for time zones, scale, and projection. I'm going to expand by clicking on the arrows, and I will go ahead and introduce this concept. So what you see here is a map of the world laid out and demarcated according to time zones. You'll notice that most of the lines are straight, but some of them are not. And the international date line here is not a straight line. The reason for that is that the other lines of the time zones are based on lines of longitude, but the international date line, which is actually at 180 degrees, is based on political decisions. And so there are some countries that want to be on one side of the international date line and some countries that want to be on the other, and that is because of time zones. So the Earth is rotating, and one of the consequences of that is that there's different amounts of sunlight reaching the Earth at different times. Also, the sun does not strike on the Earth's surface in the same way and at the same time. Therefore, each part of the Earth has a different hour in relation to the illumination of the sun. And so what you see here is with this arrow we're showing the direction of the rotation of the Earth, which is it rotates from the east to the west, and again the arrows are pointing this way. You can see that part of the globe is illuminated with sunlight and part is in darkness, which is representing night. So we can divide the Earth into 24 imaginary zones. Each of these correspond to an hour of the Earth's rotation. These are called time zones, and we use them to measure time. In general, each time zone represents 15 degrees of longitude. That is a very important rule to know as you work through the problems in this week's lab. So the reason that we come up with 15 degrees for these time zones is that the Earth is a sphere and it is 360 degrees. If we divide that by 24 hours of the day, then we get each time zone corresponds to 15 degrees of the Earth's circumference. There are some areas of the world that do not obey or follow exactly with the time zones according to geography. Notice here this is China, and China actually spans 5 different time zones if we consider it from a geographic perspective, but the political decision in China is that they follow one time zone. Again, 15 degrees of longitude is equal to 1 hour. The basis or the starting point for time zones is the Greenwich meridian. This is also 0 degrees longitude, as you hopefully recall from your latitude and longitude lab. So a clock is set forward 1 hour for each time zone to the east and back 1 hour for each time zone to the west. GMT stands for Greenwich Mean Time. Moving on to map scale. So a scale is a statement of a relationship between distances on a map and distances in real life. It is letting us know that we're not representing a real world size with a map, but we're actually seeing a reduced scale of a geographic or a real physical representation. So if we made a map with a 1-to-1 scale, it would be an exact copy of the real object, and that wouldn't be useful. But scale lets us know what the relative sizes are in the maps that we're looking at. So there's 3 primary ways that you'll see to write scale. So in this first example, it's in words. 1 centimeter is equal to 250 kilometers. That means that for every centimeter that you measure on your map, it represents 250 kilometers in the real world. If you see a scale bar, like the one pictured here, this is called scale bar or linear scale, and the distance is represented by the distance of the scale bar. Notice here that we have 0 to 5 and 0 to 10. The units is kilometers. In your lab manual, it will ask you to measure distances on your maps that are found in the back of your lab workbook or manual. If you don't have a ruler, you can use the edge of a scrap or blank piece of paper and use the scale bar in order to help you measure those distances. The third type of scale is the ratio scale, and this will be printed on the maps in your back of your workbook and in some of the examples in the exercises. Here we have 1 to 25 million, and that means that for every 1 unit on the map, it's 25 million units in the real world. These units can be anything that you measure on the smaller map. So 1 centimeter would equal 25 million centimeters in the real world. 1 inch would equal 25 million inches in the real world. So with a stated scale, this is an example showing you 1 centimeter equals 8 kilometers. We have the distance here with the yellow dotted line. And this is most useful for calculating distances. Again, remember, if you don't have a ruler, you can use the edge of a piece of paper. There are representative map scales and distances in the front of your lab manual. With a linear scale, it tells us how much map distance represents a certain real distance. For example, this scale shows that the map distance equals 10 kilometers in real distance. And so you can see here it starts at 0 and it goes to 10 kilometers. On the same map product, if you have 2 different linear scales or scale bars, you will notice that the units are slightly different. The one on the top is representing statute miles. The one on the bottom is representing kilometers. And then finally, the ratio scale. This is where we have 1 to something. And on most maps, if you'll notice here, I know it's small to see, you will have a colon. And so this is 1 to 25 million. Again, it means if you measured 1 centimeter on the map product that you're using, it would represent 25 million centimeters in real life. If it were 1 meter, it would be 25 million meters in real life. And this scale is very accurate. It can be written with a colon. It can also be written with a backward slash, which looks like a fraction. The other part of this week's lab is projections. So we're taking a complex 3-dimensional world and we're representing it with 2-dimensional products. So projecting is the science of converting the spherical Earth's surface to a flat plane. Why do we need projections? If you look at these circles on the globe, you can see in the top example, if we were using an actual three-dimensional tool like a classroom globe, if you stuck stickers on that globe, they would remain the same size and they would all remain circular. But if you were to take that globe and then stretch it out, cut it and try to stretch it out and make it into this rectangular flat product that we see down here, now you can see that the circles would actually be distorted. So along the equator, they would stay about the same size, but then as we move away, you can see they're distorted by area, shape, and or angle. And that's why we need projections. So here's something to think about as you consider projections. In this example of a perfectly square product, A and B are the same area. And this is meaning that the quadrilaterals equal in longitudinal extent formed between two parallels have equal area. But if we are taking this product and it's actually from a globe, you can see here that the areas of the quadrilaterals are not the same size. A is greater than B, which is greater than C, which is greater than D and E. Again, this globe is a three-dimensional product. This is actually a two-dimensional product. In your lab, you will read about families of projections. I want you to imagine, as you look at the definitions, of taking this diagram here as representing a piece of paper. If you were to roll a piece of paper around a globe, a cylindrical projection is going to look similar to this one that you see here. Everywhere that you would cut open this globe and unfold it and stretch it out is represented in the cylindrical projection. A conical projection is like taking a piece of paper and making a cone out of it, putting it over the top of the globe, and then transferring the information, and you would get a half circle like you see here. And then finally, azimuthal projections are like taking that piece of paper and laying it flat. So azimuthal projections are most common for looking at the North Pole and the South Pole. An example of an azimuthal projection is planar. Your book talks about a room line. A room line is any straight line on a Mercator projection. So you'll notice here that Mercator projections have right angles, and we have squares near the equator, and they get elongated into rectangles as we move towards the South Pole and towards the North Pole. Remember the stickers that we saw? That's the distortion. With an orthographic projection, these are used on perspective maps, and it's how the Earth would appear from space. A mnemonic or mnemonic map is a straight line that represents a path along a great circle. So a great circle is any circle that is a maximum distance around the Earth. One common great circle is you can think of as the equator, and then lines of latitude also form smaller circles. Okay, that's my introduction for this lab. Do your best, and remember at the end to check your answers and take the quiz.